All right, we're going to get going here. Today's problem is minimum window substring. This is day 15. I think on YouTube this is going to be listed as day 14 and day 15 because we're re-recording day 14's explanation. So if you're looking for day 14, it's actually at the end of the video. We're going to do day 15 for part of our normal rotation, and then the correct explanation for day 14 will be towards the end. I might bookmark it, or I might be lazy. Not 100% sure yet. But let's get to it. So this is our first LeetCode hard, which is kind of exciting. Let's take a look. We'll read the problem as usual, diagram it a little bit, and then I think we're going to get straight to the optimized solution today just because it's going to be a pretty long problem. And then also we got to do that second problem. So yeah, let's take a look. Given two strings s and t, we want to return the shortest substring of s such that every character in T, including duplicates, is present in the substring, and then if such a substring does not exist, we want to return an empty string. And we can assume that the correct output is always unique here. Hello, welcome in. Okay, so yes, we've got two strings. We need to find a substring, or in this case, the shortest substring of S that has all of the letters that are in T, including any duplicates. So if there's multiple letters, or if there's a character that repeats itself, we need to have a substring that has that many instances of that character. We'll see an example of that in a sec. Okay, so example one here, we've got this string here, and then this is our S, this is our T, and what we're trying to find is a substring of this guy that has all of these letters. And in this case, the shortest possible one we can find is YXAZ here. If there was an XYZ or some permutation of that, that's what we would return. But in this case, the shortest we can get is those four characters. We've got the extra A, but that's a requirement for us to create a substring that actually has all the characters we need. Okay. Next example here is kind of the exact thing that I just said, actually. If S is XYZ, and T is XYZ, then the shortest way you can get an X, a Y, and a Z is by using the whole string. So pretty straightforward there. Example 3, we've got S is X, and then T is XY. And in this case, the output is the empty string because there is no way to get XY out of the string just X, right? We don't have the Y, so there's no way to actually get a substring that has all the proper characters, so we just return the empty string. Okay, constraints here, the length of S and the length of T will both be between 1 and 1,000, so we don't have to deal with the empty string, which is kind of nice. But yeah, hello, welcome in. We're also told that S and T consist of uppercase and lowercase English letters. They don't mention this explicitly, but this might be a good question to ask an interviewer if you were being interviewed. Like, would lowercase and uppercase characters be interchangeable or no? So for example, if this was capital X, capital Y, capital Z, would we still be able to use these letters as the substring? I think the way that this problem handles it is no, and I think the test cases like don't mix uppercase and lowercase. But you know, that could be a good thing to clarify in case it's something that you need to handle. Okay, so yeah, we got a lot to do today, so I think we're going to get straight to, well, we'll do like a very brief, like, here's what you could do for the naive solution, and then we'll go straight for the optimal one. So, I did this problem on like LeetCode rather than NeetCode earlier today, so the one that I have in mind, the example I have in mind is a little bit different, but yeah, you know what, I think I've still got that one fresh in my memory, and I had an example for it that was really helpful. So the S string that we'll work with here is Adobe Code Bank. I don't know why it was bank with a C, but it was. So we're going to roll with that. And then, so this was our S. Let's say this is our S value. And then our T string, let's say, is just the last four letters there. So one way we could handle this, and I think this is maybe the easiest naive solution, would be to say, hey, well, the only way we can get a substring of S that has all the letters of T is if that substring is at least the length of T. So in this case, if we consider all of the possible substrings from 1 to or length 1 to length 13. At some point, we would hit the shortest possible one, and that would be our answer. But we don't need to start from 1, because if the substring is here, it's going to have length at least 4, right? So we could do something like, hey, let's consider this window, and then this window, and then this window. And we would keep doing that until eventually we got to the very end, et cetera, and we found this substring here, and that would be our answer. So since we want the shortest possible substring, we could do that and start at the length of the T string and just see if we got all the letters. This would probably involve like making a dictionary, at least. So like a very small optimization would be make a dictionary out of this. And then for each of these substrings, you could like make a dictionary and then slide it over as you went. So you could say like, hey, right now we have 1 of A, 1 of D, 1 of O, 1 of B. And then when you slide it over, you could say, okay, drop the A and add an E. Does it match up with the dictionary over here? If not, keep going. So next we would drop the D, add a C in terms of like the frequency counters. And at some point, either we hit the shortest possible substring that has all these letters, or it just never happens, and then we return the empty string. Why is the horse side-eyeing me? What did I do? What did I do? Okay. Okay, sweet, thanks. So that would be naive solution. Now, obviously really slow, right? Because as we talked about before, having to consider all of these different substrings is a ton of variations, especially when this string gets really long. That like number of substrings is going to blow up. It's factorial growth in terms of how many substrings we have, and that's not desirable. That's way too many iterations. So what we'd like is to be able to make kind of a smarter window out of this. And let me think. There is like, well, let me think about this. I actually want to talk about a different example string in a sec. We'll start with this one. So what you might think is, okay, we can try and we'll talk about optimizing like the actual searching and like confirming whether or not we have all of the substrings or all of the like individual letters satisfied or not. But one thing you might think, especially because we're looking at sliding window here, is like maybe we should just go ahead and like extend this window until we found all of the letters that we can, or all of the letters that we need. And then we can shrink it until we're like right on the verge of losing a letter that we need, right? So we would extend it all the way in this case, and we need to do that until we, oh, actually, you know what? This is kind of funny because actually I didn't realize this, but there's actually an earlier place we can stop. Okay, so right here we have just an A. At this point we pick up the B. At this point we pick up the C. And then when we get over here, that's the first time that we've got all the letters we need, right? So we've got the A over here, the B, the C, the N. The order is not important here, so we've just got all of them. And then in this case, if we were to treat that as the actual algorithm, we can't shrink it at all, because if we shrink it even once, we lose the A that we needed, right? And if that's where you stopped, you would think, oh, the actual correct answer is everything but the last letter. But hopefully you realize at some point, hey, you know what? Actually, if we extend this one more time, we now have the opportunity to shrink this. Actually, let me think about this. Yeah, we have the opportunity to shrink this because we've got a bunch of duplicate, or we have 2 duplicate A's, right? We've got a bunch of duplicate B's. And so basically we would just keep shifting this over until one of the counts went below what we needed it to be, right? And this is the place where we have to stop, because as soon as we pass that, we no longer have all of the like counts of T satisfied. Okay, so that's not sufficient. What we really need to do here is we need to basically extend this. Well, yeah, basically we just can't stop. We have to extend this. I guess I didn't realize it, but I just went over the optimal solution, actually. We extend this all the way till here, and that's the first time we've satisfied all the letters. And then we shrink it until we kind of hit a failure point. In this case, that's going to be... right here. So this is the furthest that we can shift that red pointer over while still having an A, a B, a C, and an N, right? We can't stop there though. Now we have to actually continue and do the same thing. So we extend to the right once, and then we shrink this until we're about to lose all the characters, like until we're about to lose one of the characters that we need. So moving it over here is fine because we had two C's, right? And then we can keep going because these guys aren't in the T string. We get here, and then at this point we have to stop because if we were to shift it over anymore, we would lose out on the B that we need. And so we stop here, or I guess either here or here, but somewhere around there. And then when we try to extend one more time, we're at the end of the string, so we can stop. So basically we have to repeat this process of like lengthening the window until we have something valid, and then shrinking it until the moment that it goes invalid, and then we lengthen it again until it becomes valid, and so on and so forth. So string T is going to be the letters that we need to be present in the substring of S. So having it be B-A-N-C tells us the substring of our answer has to include all of those letters once. Yeah. I don't know why it's that. That's just what the LeetCode example was, and I've been thinking about it all day. So yeah. Anyways, so yes, that's the overall process. Again, we lengthen the window, so we move the right pointer over, and as soon as we have a situation where all of the letters are satisfied, we are going to shrink the window until the moment that it goes invalid. Okay, and then we'll lengthen the window until we have another valid string, and then shrink the window until the moment that it goes invalid. And as we do that, we'll have to track kind of what the substrings are, or we'll just track the shortest. So if we get something that's shorter than what we've seen before, we'll replace it. And if it's longer than it was before, we don't care. We'll just keep looking. Okay, so one of the challenges here is like, how do we efficiently determine whether or not we have a valid string? I think like the intuitive way to do this that is a little bit slow is to, and this is still a decent optimization here, but you would say, hey, let's make a counter over here. B occurs once, A occurs once, N occurs once, C occurs once. And then we can, like as we slide along, make a counter out of the substrings that we're looking at. So this would be like A occurs once. And basically every time we add on a letter, we would say like, ooh, are these two the same? And or let's loop through. I guess the assumption here is that T is shorter than S. So I guess the direct way to do this would be like, let's look at all of these letters and see if all of their counts are present here. Now that's obviously like, we'd like a better way to do that, because if we don't have a better way to do that, we have to look through every single one of these letters every time we add on a string, as well as every time we move over that left pointer, we have to see like, are every single one of the counts correct? And if this is a really long string, you know, add on the rest of the alphabet here and more, that's going to be really inefficient to have to look through that entire string, or all of the counts for that string. I guess it's a maximum of 52, because it could be 26 lowercase letters and 26 uppercase letters, but having to do 52 operations every time we move one of these pointers over, and then, you know, this can be up to 1,000 characters, that's going to take a really, really long time. So we'd like a better way to figure out if we have like a valid string or not. And here's one way we can do it is we can still keep the counts over here, but we can separately say, okay, so actually let me label these with some names just so I can refer to them. These are the counts that we need. We can say this dictionary is like the counts that we have. And in addition to that, what we can also say is, hey, let's keep actually a track of which letters have been, or how many letters have been satisfied. So when we begin, obviously it's 0 because we haven't added any letters yet. But instead of having to look through everything, we can basically just say like, hey, once a letter hits the count that it needs to be, so once this count is the same as it is over here, we can increment that satisfied counter. Okay, so we'll just play this out in the interest of demonstrating it. So we would add on the A, We know that we don't have a valid string yet because the satisfied count isn't appropriately high. Speaking of which, how do we know when satisfied is the right number? Well, it's just whatever the length of this dictionary is, right? So once we have 4 characters satisfied, that's how we know we've got a valid string, right? Okay, so just to recap that, once this count is equal to this count, we know that we've satisfied one of the letters. Once this satisfied count is equal to the length of this dictionary, we know that we have a valid string, right? Okay, so let's just play this out real quick. We move this pointer over, we add the D. Now that's not one of the letters over here, so we don't have to worry about that one. But certainly we aren't going to increment satisfied. We add an O, and I guess this is kind of optional. We don't need to track the letters that aren't in the need dictionary, but I'm just going to do it anyways. Okay, O is 1. Now we add in the B, and again we check, hey, did this just meet the criteria, or did this just satisfy one of the letters over here? Well, this count is equal to this count, so that means we're good. We can increment this, and now 2 letters have been satisfied. And notice, like, we don't have to look through either of the dictionaries in their entirety to figure out, if we've met the satisfied count. Okay, so we keep going. E is 1. We don't really care because it's not part of the need dictionary. We get C, and this one actually does matter. So you can see that this matches that, and this means we're going to increment satisfied by 1. So now we have 3 letters satisfied. We are aiming for 4. The O changes this to a 2. The D gets added. The E changes this to a 2. Okay, and then the B. Okay, so actually this is a good moment for us to stop here. This B increments this by 1, but we don't really care because having duplicate B's doesn't help us to satisfy more letters, right? So we only care about incrementing satisfied when we hit the count, okay? And since we keep moving over and adding letters, we don't have to worry about like going below the count either. We're always going upwards, so B hits 2, that's fine. It doesn't satisfy another letter. We just have some backups now, which is kind of nice because it gives us more flexibility when we move the other side of the string over, or the other side of the window. Okay, similarly, we get this duplicate A. We don't have to change anything for that. And then finally, we hit this N, and at this point we go, ooh, the count for N just reached the count for N in the need dictionary. This means we have 4 characters satisfied, and this means we can at least attempt to shrink the window, again, until the moment that it goes invalid. Okay. So let's give it a shot. So at this moment we say, okay, I need to shrink the window just right up until it goes invalid because that's the shortest possible string that we can make that still has all the characters, right? So this time it's the other way around. If we get rid of a letter and that causes the count that we have to go below the count that we need, then we're going to say, okay, we have 1 less character satisfying than what we need, and we're going to have to call it quits at this moment, right? So for example, right here, the left pointer is pointing at A. We're going to decrement this by 1, which is fine. It hasn't gone below what we need, right? And then shift this guy over. Okay, so at this moment, we still have a valid string, right? Decrement the D. That's not even in the need dictionary, so it continues to be valid. Decrement the O. Okay, decrement the B. Again, that's not less than what we need, so we can leave it. Decrement the E. Decrement the C, and this is actually the moment that it goes invalid, right? So CODEBAN is actually a valid substring. At this moment, we would probably want to say, okay, let's see if that's the shortest thing we've seen so far. And it is, because it's the first thing we've considered. And so what I'm going to say, just because we don't want to store too many strings, because again, in Python, they're immutable. Takes a lot of computational energy to make a bunch of strings and strings and strings and strings. Instead, what we can do is we can store these indexes. So this would be like 0, 1, 2, 3, 4, 5. And then 6, 7, 8, 9, 10, 11. So these are the indexes of the shortest substring we found that still has all of the characters that we need, right? It has an A, it has a B, it has a C, it has an N. Okay? At this point, it's as short as it can be, and in fact, in terms of the code, we'll even shift this over by 1 again, because we actually want to start with something invalid so that we're ready to tell when it becomes valid again. Right? If we start with it valid, then it's like, well, we know it's valid. That doesn't help us, right? So we're actually going to move that pointer over 1 more to say, I know that at this moment it becomes an invalid string. Let's see how far we have to shift this over again until it becomes valid. Okay, and in this case, it's pretty quick. We shift this over, and then we regain the C that we lost. Sorry, a second ago, this went down by 1. That's what tipped us off to the fact that we should check if we got a good answer. We shifted it over. It became invalid. Now we shift the right pointer over. Oh, I forgot. Sorry, this was supposed to be a 0. I don't know why I wrote 1. Because this was a 0. Satisfied actually went back down to 3, right? Okay, now we add in the C. Sorry, I like really messed up the diagramming there. Now we add in the C. This guy matches up with this guy. That means that we've satisfied another character. This goes back to 4, and we repeat the process now of shrinking the window from the left. So get rid of the O. Shift over. Get rid of the D. Well, how did that go? Oh, you know what? I never added in the D in the first place. Anyways, the D, we get rid of. It's now at count 0. I'd be messing things up. It's what it is. Okay, we decrease the E by 1. Okay, at this moment, if we were to get rid of the B, right, which we only have 1 of, we would become invalid again. So we pause here. We see, hey, is this a shorter length than what we saw before? It actually is. The previous string was length 7. This one is length 4. So we'll replace these with the better indexes here, which are 12 and 9. Okay. Again, at this moment, it's valid. We're going to shift it over by 1 to make it invalid again, but we're at the end of the string, so we're good. Okay, and that's actually the overall algorithm. We'll get to the code right now, because, God, I've been talking for 25 minutes. It's a lot to talk about. But in short, this satisfied counter is going to be really helpful for us because we don't have to look through all the letters. We can just track them as we go. As soon as, while we're shifting the right pointer over, if we have one of these letters match the count over here in the need dictionary, we can increment satisfied. And then as we move the left pointer over, if we're about to lose one of the characters that we need for the whole T string to be satisfied, that would mean that the count over here is 1 less than the count over here, right? Okay, God, so much talking. Let's get to the code. Let's get to the code, y'all. Okay. So we need that T dictionary, which I'm going to call need. Okay, so for each character in T, we're going to say need for that character is go ahead and get what it was before. And if it wasn't there, use 0, and then add 1 to it. Okay, the left pointer we'll say starts at 0. We need like a satisfied count, which also starts at 0. And then I think we can leap into the 4. Oh, we also need the result. Okay, so for the result here, again, we're storing like a left and a right index just so that we don't have to repeatedly write strings. What we want to start with is something that is longer than the answer could possibly be, because we want to like always choose the minimum. So as soon as we get an answer, we'll replace this. But I'll start by making it 0 to the length of S. Yeah. Well, just for good measure, I'm going to say length of s plus 2, because it's definitely never going to get there. If we were there, then we would be talking about something that's longer than the original string, which doesn't make sense. Okay. Now, I think we can roll with a for loop, because that right pointer is just going to move over by 1, and then within each of those loops, like, we may need to shift the left pointer over, but we'll say for right in range length s. Okay, so we're going to go through each of the letters here. So we'll say, oh, we also need a have dictionary. So have for the character at the right index, we're going to use that same trick as before, is whatever it was before. Ooh. If not, use 0 and then add 1 to it. Okay, so at this moment, we might have just hit a point where we have a valid string. So we can say if have sRight equals need sRight. Okay, so this is if the character is actually in the need dictionary. If not, this is gonna be a problem because we can't access something that's not in there, right, in terms of the dictionary. So I'm going to preface this with if sRight is in need in the first place. And then assuming that that works, if we just hit the count that we needed, so yeah, if we just hit the count that we needed, then we can increment satisfied by 1. Okay, so at this point now, I'm going to say, well, we might need to move that left pointer over repeatedly. So I was going to say if satisfied equals the length of need. But actually, we want to keep doing this until we hit the invalid string, right? So I'll say while satisfied and the length of need are the same, what do we need to do? Well, we need to decrement the count at the left index, right? So have, wait, hold on, let's think about this. Yeah, have, so we know that this will actually be in there because the only way we can be removing it is if we added it in the first place. So have at s left minus equals 1. And then if, and then same trick as before here, if s left is in need. And so what we're trying to capture here is if we've now become invalid, or we're about to become invalid. And that would be the case if have, so the number of s left that we have is now less than the number of s left that we need. Okay, now the other thing here is if we're in this loop, we know that originally the haves and the needs were all equal to each other, at least for the things that are actually in T, right? Ooh. Hello? Okay, so we know that if we're in this loop, originally they were equal. We decrement this count by 1, and now if it's just dropped below what we need, we're about to have an invalid string, right? Or we do have an invalid string, I guess. We haven't moved the pointer over, so like it's not invalid yet, but according to the have dictionary, it's invalid. Okay, so at this moment we can say, okay, it's possible that this is our solution, right? We'll say res. Oh no, we need a condition here. Okay, if s left in need and have s left. Okay, am I really gonna write an if inside an if here? Yeah, I guess so. Well, okay. So if right minus left plus 1. So again, this is the length of the string, right? So if the length of the substring that we're looking at right now is less than the length of this substring, whatever was stored in res before. So I'll say res 1 minus res 0 plus 1. Well, I guess we don't need to do that, huh? Because, well, like, think in terms of algebraic inequalities. You can just subtract 1 from both sides, right? Okay. So assuming that the difference between these is smaller than anything we've seen before, then we'll replace it. Okay, and then now we can say, hey, well, actually, you know what? I think this is better suited to right up here. Say satisfied is decreased by 1. That was the thing that tipped us off to the fact that it became invalid. Replace result if needed. And then move left over. Okay. If that was, so if moving left over did invalidate the string, we're now going to exit this while loop, and then we're going to increment right until we have something valid, shrink it until it becomes invalid, and so on and so forth. And that should be it. Okay, so what do we need to return here? We actually need to return the substring itself. That is like the minimum window. So we'll say return s. Okay, so here's where it gets weird. String slicing, it excludes the last character, but we want to keep it, right? Because it's actually part of the answer. So we'll say s sliced from left to right plus 1. But only if we actually got an answer, right? So it's possible we went through all of this and it never gave us a valid substring. So I'm going to say return that if res does not equal what it was originally. But if it does equal what it was originally, return the empty string. All right, let's see what I messed up. I probably messed something up. Okay, what is it? Something equals 0. What? Did I spell it wrong? Ooh, I spelled it wrong. That is so sad. Oh, she don't work. Okay, let's take a look. Oh, I think I'm just slicing it weird. Well, let's see if the other answers were like that. Yeah, I think I've just sliced something off here. Left equals 0. Let's take a look. So right here, this is where we did the replacement. Is if f's left is in need. Okay, so this is the moment it becomes invalid. Satisfied minus equals 1. If... Oh, no, not left. Not left. This is not supposed to be with left and 1. This is supposed to be res 0. So, sorry, I was using left and right, but by the end of the algorithm, we might just have a bunch of invalid stuff, right? So that's actually not something we want. We want to use the result, right? So res 0 to res 1 plus 1 is what we want here, assuming that we ever replaced it. Okay, whew, that one worked. Please, God, please. Okay, she works. Sweet. Okay, so that is day 15 here. That's minimum window substring. Great. Oh, that was such a relief compared to yesterday. Yesterday was stressing me out. Speaking of which, I'm not going to keep you guys here, but I do owe the people a recording of yesterday's problem. So actually, that's what we're going to tackle now. So if y'all want to stick around, you're welcome to. If you don't, I totally understand. This is a whole ass class at this point. Any questions on day 15, though? At all? Anything I can address? Sweet. Yeah, it's kind of a fun one. And I will say, like, the optimizations are mostly around this whole, like, satisfied characters thing. You can totally do this, and it works just fine if you just look through the dictionaries and compare them. The satisfied thing is just a nice trick. All right, let's look at yesterday's question. Because there was something stressing. I was writing this solution, and we got here, and I went, that don't make no sense. And there's a really good reason it didn't make sense, because it's not at all doing the thing that it suggests it does. Okay, so we're officially in day 14 mode now. We actually did cover a bunch of good stuff yesterday, and so we'll very briefly recover it and then talk about one place where the algorithm we talked about yesterday didn't make sense. Okay, so just to recap the problem a little bit here. Oh, you know what? Actually, we're not posting yesterday's recording. So I'm going to read through the problem, we'll work through an example, and I'll describe the correct algorithm this time. We probably won't do the naive solution. Okay, so longest repeating character replacement. We're given a string S consisting of only uppercase English characters and an integer k. We can choose up to k characters of the string and replace them with any other uppercase English character. And then after performing at most k replacements, we want to return the length of the longest substring, which contains only one distinct character. So day 13, we wanted, what did we want on day 13? No repetitions, I think. This is the opposite. We want all repetitions except for a select limited number. And so, for example, x, y, y, x with k equals 2 means what's the longest substring you can make that has all the same letter, assuming you can replace 2 of them with whatever you want. Okay, so we can either replace these two y's with x's and have x, 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 x for a length of 4, or replace the two x's with y's and have y, 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 y also for an output of 4. And notice we don't care about the substring, we just care about the length. Okay, A, B, B here with k equals 1. The output is 5 because this string right here, we can replace the B and we get 5 A's in a row. And the longest we can get, assuming that we use the B's as the main character here, is 4. So the output is 5. Okay, so let's very quickly get through this here. I'm actually going to use this as our guide. 3 A's, B, A, B, B. Okay, so the overall algorithm here is actually as described before. We want to use a sliding window until we get something, like we'll expand it as long as it's valid, and then as soon as it becomes invalid, we have an action to take, so to speak. Let me actually, I'm going to extend this with that. Okay, so here's what we'll do is we will track whatever the maximum frequency is. Okay, so here's where I got tripped up yesterday. I thought we needed to update this anytime the maximum frequency changes. Turns out what this really represents is the maximum frequency overall that we've seen so far. And there's a really good reason for that we'll talk about in a sec. But in short, we don't actually care what the maximum character is. We just want to know how many times it occurred. Okay, and we can track that using a counts dictionary. Okay, so when we start, we'll say, hey, go ahead and increment the count of A by 1. So it wasn't there before, now it's 1. We haven't needed to do any replacements, but yeah. Well, actually, we should talk about that first. One of the questions is, how do we know when the string becomes invalid? Well, here's the really important relationship. The string length, which is just right minus left plus 1, and the maximum frequency, these are like very closely tied together, because whatever the maximum frequency character is, if you take the string length minus that, you need that to be less than k. So if the string length is 6, for example, and the maximum frequency character happens 4 times, k is 1 here, this would tell us that we have an invalid string, right? Because we're only allowed to have one replacement, but if the length of the string is 6 and the most frequent character occurs 4 times, we would need 2 replacements for them to all be the same, right? So this is like the core relationship, and the problem is the string length minus the maximum frequency. In order for it to be a valid string, has to be less than k. I just noticed I've been talking really fast. I'm going to slow down just a tiny bit here. Okay, so with all that being said, we add in A with a count of 1. The string length is 1. 1 minus 1 is 0, so we're good right now, right? We hit this A. The count becomes 2. 2 minus 2 is 0. We haven't had to make any replacements so far, so we're good. Okay, we add in another A. We have a count of 3. 3 minus 3, so string length 3 minus count of A is 3, is 0. Okay. And then we get over here. Notice the maximum frequency overall right now is 3, right? We add in this b, so we'll add it to the dictionary here. The string length is 4 minus the maximum frequency is 3. That's 1. Oh, just kidding. Less than or equal to k, because we're allowed to make k substitutions. So 4 minus 3 is 1. That's fine in our book, right? Because we're allowed to make one substitution, so we keep going. Okay, notice we didn't update maximum frequency overall because it didn't increase, right? This guy is still 3. And also note, whatever character it is that we just added on, that's the only one that can become the new most frequent character, right? As long as we're sliding over to the right. So B had the possibility of kind of overshadowing A, but it didn't. So we keep going. Okay. Now we increment this count. And notice the count of the thing that we're looking at right now is 4, which is higher than 3. So we'll replace maximum frequency overall with 4. Okay, and string length 5 minus maximum frequency 4 is 1. Yes, exactly. So it's the highest count of a single letter that we've had so far. Okay, and then so 5 minus 4 is 1. That means it's still valid. But then we get here, B goes up to 2. And now 6 minus 2, or 6 minus 4 is 2. That's higher than what we're allowed to replace. So alarm bells, this becomes invalid, right? So here's where I was tripped up yesterday. What I told you guys was we need to slide the left pointer over until it becomes valid again. Here's the problem. We don't know what the maximum frequency character is. We just know what the frequency of it is, right? And dictionaries are not good at going backwards. It's really easy to find a key and know what value it's associated with. But in order to find a value and go to the character it's associated with, we have to look through potentially all of the values, which is slow, right? It works, but it's slow. So here's what we really want to do. We know, because it just became invalid, that the largest window we can make is length 5, right? So it doesn't make sense for us to shrink the window all the way until it becomes valid again. Let's just keep sliding it over until we can find a wider window. So this is the core. Is to do that, all we need to do is slide this over by 1. This is not a valid string, but we don't care because we already know what the length of the longest valid string we've seen so far is, right? So when we were over here, we knew it was valid still. It was length 5, right? I didn't actually mention this, but we store that somewhere. And then when we get here, we know that it's become invalid, but we don't need to move this over until it becomes valid again. We can just slide it over by 1. We don't care if this is valid or not, but here's the thing. As long as we keep doing that, so shift over, and we keep that window the same length, the only, how do I phrase this? As soon as something else takes over as the most frequent character we've seen so far, that validates our ability to get a wider window because of this equation here, this inequality. If maximum frequency overall goes up, that means we can now make a window that is wider than any window we've seen before. Okay, so we don't care if the intervening windows are bad because we only care if that number goes up. So this is not a valid string, but we're still going to use that as the window until such a time as something takes over, in this case B, as the most frequent overall. So let's continue playing it out so that it hopefully becomes even more clear. We decrease the count of A by 1 because we shifted this over, right? So we shift this over. That makes this go down by 1. So now it's 3 A's, 2 B's. That's fine. But in this case, okay, hold on. Let me say it this way. We don't even care if this is a valid string or not. We just want to know if we can beat the maximum frequency overall. So we decrease that by 1. Yeah, we shift this over. We increase the count of B by 1. So still nothing has taken over as the most frequent character we've seen so far. But because we want to keep the window the same length, we shift this over by 1, which decreases the count of A. So now we have 2 A's, 3 B's. We do it again, increase the count of B. Okay, now this is equal to maximum frequency overall, but that doesn't mean we've got a better answer, right? And then we decrease the count of A by 1. So now we have 1A and 4 B's. This is the moment where something important happens. As soon as we get here, we increase the count of B by 1, and that's now the most frequent character we've ever seen. Which also means we have the possibility of making a wider window than we have made before that is actually valid, right? So we replace maximum frequency overall with 5. This now, when we evaluate this, the string length is 6 minus the maximum frequency is 5, which is equal to 1. So we know that we have a new valid string. We can update our widest possible window, or the length of our widest possible window at this point. And it doesn't happen until we encounter something that occurred more frequently than the A's here, right? So up until this point, we had a most frequent character of 4, which let us have a window length of 5. It's not until we get to this point that we have a most frequent character of 5, which means we can have a window length of 6. Okay, so all of the intervening windows here before we got there, so everything from like here, everything from here onward, these were all invalid, and we didn't care because we knew that in order for us to improve the answer, we needed to have something occur more frequently than 4 times. So we have a bunch of invalid windows until we get to such a point right here that we had something occur more than 4 times, and now we can say, ooh, we know that it's valid now. We can replace the answer, or the kind of the running total so far. Okay, and what this means is that while loop that I was talking about yesterday, if you were around for that, wasn't really a while loop after all. It was just checking if we should keep the window the same length as it was before. So it wasn't validating the string. It's not saying let's move left over until we have something valid. It's just saying move it over by 1, and then keep it going until you find something that's wider than it was. Sorry. Move the left pointer over by 1, and then shift the window until you find a new candidate that will make the window wider than it was before. In this case, the new candidate is B. Okay. I'm gonna get to the code because God, it was a lot of talking, and I'm really hungry. I haven't had much to eat today, so let's get to it. Okay, so I'm gonna say max frequency overall. We'll start that at 0. Left is gonna start at 0. Is that it? Oh, we need a counts dictionary. Okay, and then now we're going to go through, and again, that blue pointer, the right pointer, is just going to move over by 1. Assuming we still have a valid string, we'll keep moving it, and only if we realize we have an invalid string do we need to move the left pointer over. Okay, so I'll say for right in range length s, counts for s right is going to go up by 1. So same idiom here as before. Okay, so increase the count of s right if that count is greater than the most frequent character that we've seen so far, however many times that occurred, then the new max frequency overall is that number. Oh, actually, you know what? We don't even need this because we can just say this is going to be either what it was before, or if the counts at s right is bigger, replace it. Okay. Now at this point, it's possible that that didn't happen, right? So this might stay the same as it was before. If it stayed the same as it was before, that means we still have an invalid string. We'll say if right minus left plus 1. So the string length, I'll put this in parentheses to make it more obvious, minus max frequency overall. If that is less than? Oh boy. So this represents the number of replacements that we need to make, right? We need it to be less than or equal to k. So in other words, yeah, what we want to actually check here is if it's invalid, then reduce the count of whatever's at the left index. And this time we can just do it directly because we know that if we're accessing it, it was added into it before. So assuming we have something invalid, reduce the count at s left by 1 and move the left pointer over by 1. And we just have to do it once because assuming that this actually happens, we just want to slide the window over at the same width that it was before, right? Again, waiting until we have another candidate that has more frequency than the previous candidate. Okay, and so we just do that once, and then we also need to check if the result... Ooh, actually, we could probably check this a little bit more smartly. Well, okay. I'll just have a result here. I'll set result equal to 0, and we'll say result is whatever is bigger between right minus left plus 1 and the previous result. Okay, and notice we're actually gonna hit that block for a bunch of the intervening windows that are invalid, but that's fine because in order for us to have that width of window, we had to see something that was valid before that was that length. So we'll like kind of overwrite this, or like we'll hit this and kind of replace, well, yeah, if this isn't bigger, we're not going to replace it. So this is actually fine for us. We have a bunch of invalid windows that are the same length as res, but we're not going to overwrite because it's the same length. Okay, and I think that should do it. I think at this point we can just return res, but my brain is like running on fumes right now, so that this might not actually work. Let me think about this for just a sec. Yeah, so this is the character we've seen with the most frequency so far. This starts at 0. This is the counts that we've seen in the current window. The original result value is 0, which is great because we want to maximize. Yeah, we could technically set it to 1 because I think the string is at least length 1, but whatever. Okay, and then yeah, so we move right over, that's part of the for loop here. Increase the count for right. If that's bigger than anything we've seen before, replace it. Okay, now if we have an invalid string still, then we just bump the window over by 1. And then we see if this is the widest window so far. So I think that should work. Oh, thank God. Why is it empty? Okay, and then let's submit, please. Okay, it worked. Thank God. Okay, so yeah, this is the weird part, and I think most of the solutions that I've seen, they write while here, which is weird because it's not a while loop, and it's not. I think like people, and this was me actually. I used to think, hey, this is actually slide left over until valid again, and that's not true. We actually have a bunch of invalid strings, and all this is really doing, and this is actually a great place for a clarifying comment. If it's invalid, keep the same width and shift over is what this really does. Right, the right moved over by 1 here, this moves the left over by 1. And we only do it once because we are saying, let's keep the same window and slide it over until we can widen the window, right? Okay, yeah. It might be good, and this might be a good comment for posterity in case I come back to this later. We only care to replace if this new contender, is that how you spell contender? Contender? Yeah. We only care to replace if this new contender happens more frequently than anything we've seen before. And again, the core of this is the window length is directly related to the most frequent character. So we only care to replace it if this is the highest frequency we've ever seen. So in the example, the highest frequency at the beginning was 4, and by the time we get here, the highest frequency is 5, which allows us to widen the window. Okay, under an hour for 2 problems. That feels good. That feels like good timing. Thanks for sticking around, y'all. It's been fun. I'm gonna kill the recording there, and I'm gonna go eat some dinner. But you guys have a good night, and see you tomorrow if you can tune in.